Introduction of exercise 1.4. So the first thing that we will discuss is Venn diagrams. Venn diagrams. Now these are the diagrams that give us an easier way to represent various operations on sets. For example, let us say, and there is a particular way that we use these rectangles. We use rectangle to represent the universal set. So for universal set we use a rectangle, and we used some closed curves and generally circles to denote sets that are part of these universal sets, right? If let us say I've got a universal set that is the biggest or the basic set, out of which I will take some sets and do some operations on these sets. So these are, all of these sets are obviously the subsets of this universal set, and these sets are represented by circles like this. Okay, this may be, let us say, set A, and then there can be some other set B, there can be some other set C. Okay, now B and C here have some common area also, right? They may have a common area. Okay, some common elements may be there in set B and C. We will understand about this while we do union and intersection of sets. So Venn diagrams will be widely used in this chapter to represent the sets, to represent various operations on sets, also for problem solving. Sometimes very difficult looking problems can be solved very easily using Venn diagrams. All right, so next let us see what are the operations on sets. Operations on sets in general, till now in number system, etc., or in algebra, you have studied about these operations like addition of numbers, right, subtraction, etc. So on sets we have got some operations like union of sets. Union of sets, let us understand this first, then we will write the definition. Let us say there is a set A containing elements 1 and 2, and there is another set B that contains elements, let us say, 1, 3, 5. All right, now I want to find a set, right? I want to find a set which has got all the elements of A and B, right? But I do not need the common elements, okay? Because in a set, obviously we do not write the elements repeatedly, right? So I need a set which has got all the elements of A and B, right? So let us see. If I write a set, let us say I am denoting a set by this, and I write all the elements that are there in set A and that are there in set B, but I am not repeating the elements. One is being repeated, so I am not writing that. So this set here is known as A union B. A union B, where in A union B is also a set, right? So A union B means that we will take all the elements of set A and all the elements of set B and write it in a set, and we will obviously not repeat any numbers or any elements, because that is what we do in sets, right? We do not repeat. So common elements are not to be repeated. Now this is a union of sets, and there is a sense of or in this, right? Why? Because I can write this in, let us say, this form: x such that x belongs to set A or x belongs to set B. If I write like this, that x belongs to set A, there is an element which belongs to set A or set B. So all these elements, 1 belongs to A, 2 belongs to A, and 1 belongs to B also, right? It should either belong to this or belong to this. All these elements will be taken. 3 belongs to B, 5 belongs to B. So all these elements are to be taken, and this is the roster form and this is the set builder form in which it is written. So OR will give me the sense of union of sets, right? Then there are some properties of union of sets. I hope you have understood why I have written OR here. Whereas while defining I said we will take all the elements of A and all the elements of B, barring the repetition of elements, of common elements, of course. So I was using that and in terms of English language, that all the elements of A will be there, all the elements of B will be there, repetition will not be allowed. But if you see mathematically, it gives you a sense of OR, that either that element should be present in A or that element should be present in B. That means all the elements of A will be taken, all the elements of B will be taken, and repetition obviously is not to be taken. Now there are some properties of union of sets. Properties like commutativity, you have studied about these properties, commutativity in your junior classes also. So if there is A union B, it is also equal to B union A. Now A union B means all the elements of A and B except the repeated elements. So B union A also means the same, all the elements that are there in B and A except the repeated elements. Okay, or in other sense it means X such that X belongs to A or X belongs to B. You can exchange these, right, interchange these, so it will give you B union A. So A union B is equal to B union A, that is the property of commutativity. Then there is associativity, which means A union B union C is equal to A union B union C, right? You can also check this, that elements of A or B, then you take union with C, it will be equal to this. This is property of associativity. What we can do is we can verify these properties by taking, let us say, 3 sets A, B, take some common elements and take some uncommon elements also, so that you can arrive at a more general result. Let us take 5 here and then take 1, 7, 9. Now what you can do is you can apply these commutativity, property of commutativity, property of associativity, and verify these results yourself. I leave this as an exercise for you guys. Okay, so 2 properties, commutativity, associativity, and then we take union with phi, union with the universal set, and union with itself, right? When we take union with phi, right, we write all the elements that are there in A and that are there in phi, but there is no element in phi, right? So we will be writing all the elements that are there in A. Okay, so this is nothing but an identity element because it returns me A itself, the identical result. Okay, so A union of a set with an empty set will return me the set itself, and A union A obviously will be A because I won't write the repeated elements. If I need to take the union of these sets, I will write all these elements and all these elements, but these elements are already written here. So A union A is nothing but A. And when you take union with universal set, obviously you will get a universal set in return, right? Because let us say this is the universal set and there is this set A inside it. When you take union, you mean you need to consider all the elements that are there in the universal set as well as the elements that are there in the set A. So if you see all the elements of universal set, or the universal set itself will be the answer. Okay, so this law has a special name, idempotent law. Okay, now we will talk about another operation, that is intersection of sets. Intersection of sets. Now in this operation we will consider only the elements that are common to both the sets. Common to both the sets, right? So there is a sense of and while taking the intersection, and how we denote the intersection? By this inverted U, right? This is the symbol that we will use. So it will give me, let us say if I take A intersection B, it will give me the elements that are common to both the sets A and B, right? And what did my this operation union gave me? The elements. This comparison is necessary, right? So that you know the difference. The elements that are there in set A or B, right? Now this means and this and means that we will need only the common elements, and this or means we will take the common elements as well as the other elements also that are there in A or B. Okay, so let me apply both the operations on these sets. If let us say this is A, E, I, O, U, and let us say this is set B, which is A, B, C, D, E, and now if I apply the union, I'll have what? I'll need to take the elements that are there in A or B. A or B. So this is in A. These elements are there in A. So let me write the elements that are there in A. So all these elements will be considered. Or B. So I'll take the elements that are there in B. Okay. So B is there in B. E is there in A. So the element should either be present in A or it should be present in B. All these elements will be considered. Now I have considered these elements. A is present in B, but I have already taken it, so I'll avoid the common elements. B is present in B, so I'll take it. C, I'll take it. D, I'll take it. E, I have already taken it, so I will not write the common elements once again. This is A union B, right? And now let me write A intersection B, and I'll explain why it gives a sense of and. Now A intersection B, if you write, that element should be present in A and B simultaneously. It should be present in A as well as B. Okay, so which are the elements that are present in A as well as B? A is present in A, in B. U is not present there. E is present in A. E is also present in B. So A and E elements, these are the only elements that are present in A as well as in B. Okay, so these should be present in A as well as in B. These elements here in union should be present in A or B. Okay, if it is present in either of them, right, either one of them, then it is okay for us in union. But in intersection we require it to be present in both the sets. Only then it will be considered in the intersection. Okay, so let me write some properties for intersection. First property, we will write again the property of commutativity. So it applies here also, because common elements of set A and B are same as common elements of set B and A, right? And there is another property that we discussed, was associativity, right? A intersection B intersection C. A intersection B intersection C. Excuse me. Now this is the property of associativity. So if I do A intersection B and then take intersection with C, or if I take intersection between B and C and then take intersection with A, both will give me the same result. This is commutativity, this is associativity. Now other properties that we did discuss while discussing the union were, we took the we took the union between A and A, so we will do the same in intersection. So A intersection A, intersection of A with phi, intersection of A with universal set. Let us discuss these. So if I want to know the common elements between set A and set A, so obviously these will be all the elements in set A. Okay. If I want the common elements between a set A and the empty set, what will be the common elements? Let us say I give you two sets, right? What are the common elements in these? Now in the empty set there is no element, so how can there be a common element between these two? It will not be there, so it will return me nothing, so it will return me an empty set. Okay. Now if I take intersection of A with a universal set, think about it using a Venn diagram. So let us say I've got this set A. Now what is common between this universal set and this set A? This entire set A is common to both. Like this is set A, and this set A obviously is there in this universal set. So what is common? This set itself is common. Another important property is distributivity. What I mean is, if I have something like this, B union C, so this intersection can be distributed over union. So I can write it like this: A intersection B union A intersection C. So this is property of distributivity. Okay, this is idempotent law, this is intersection with empty set, this is intersection with universal, and this is distributivity. Okay, so these are some of the properties of intersection. So I want to visualize these operations using these Venn diagrams, right? This is a rectangle and inside it I've got some circles. So first thing that I want you to visualize is B union C. So what does that mean? That means that element should either be present in B or it should be present in C. We will take all these elements, right, which are present either in B or in C. So the area that I'll take is this. The element should be present in B. This entire B is taken, or it should be present in C. So this entire area is also to be taken. This area that I have shaded with this color red is B union C. Okay. Now in this diagram I want A intersection B. So I just want the area common between set A and set B, or in other words, I want only the common elements of set A and set B. So which is the area common between A and B? This is the area, right? So this is the area that gives me A intersection B, and this area gave me B union C. Now let us look at this one. I require A intersection B, so the common area between A and B, and then I'll take union of A intersection C, which is common area between A and C, where this was A, this is B, this is C. So common area between A and B is this one. Okay, and I need to take intersection with union with A intersection C, which is common area between A and C, which is this. So all this area, right, is to be considered. Okay, I hope it is very easy to visualize. All right, now let us think about this diagram here. A intersection B union C. Now I need common area Now B intersection C will give me the entire area in this circle and entire area in this circle, but I need common area with A. Okay, so in this circle and in this circle, if you see, the common area with A will be what? This area and this area, right?